thank Professor Carty for showing me your facilities here. You are living in the seventh cloud, I say. It's a very nice organized infrastructure. And also the idea of having the seminar actually came during our summer discussion with Beck, so it's a little bit like a late decision. So again, thanks Beck for allowing me to share with you some of stories of research that I've been involved in Sherbrooke. So for those that are not familiar with geography of Canada, Sherbrooke is roughly 1.5 hours east of Montreal and 4.5 hours north of Boston. So there are two universities there, Sherbrooke University, 30,000 students plus, more than 30,000 students, and then there's another Bishop's University, which is more less science, but more human domains. Today what I would like to talk is photocorrosion of functionalized gallium arsenide, aluminum gallium arsenide nano-heterostructures. But let me begin first with a couple of slides. I'll tell you a little bit about our facility so you have also some perspective. So we have roughly 40 profs and 100 graduate students involved in so-called interdisciplinary Institute for Technological Innovation. So this is a little bit of main campus, 1.5 kilometers from main campus of the university. And the idea here is to work on technology transfer and on collaboration with industry and public and private organizations, particularly in sectors such as healthcare, information and communication, transportation and energy. We have clean room facilities. Without going into details, basically, we can fabricate ridge waveguide lasers on 3-5 materials. And we teach students 3-micron technology based on nitride, on nitrogen oxides, and on silicon oxide technology we develop based on nanolithography structures down to tens of nanometer scale. So this facility serves also as a node for some other users from Canadian universities, but also from industry. I'm particularly, since I joined university in Sherbrooke, I have been involved in developing infrastructure involving application of lasers for processing of materials. And I would summarize this in three directions: laser-based bandgap engineering, physics and chemistry of laser process surfaces, and quantum semiconductor biosensors. So today, basically, what I would like to focus on is talking about this third domain of my activities. Just a couple highlights. What we do, for instance, with lasers, we have a system that we develop for rapid thermal annealing using two different laser sources. And so we can heat any wafers that you want to near melting point temperature if required. But the trick here is that you can bring, using this light emitting diode, you can bring temperature of the wafer up to near the threshold that is of your interest, and then use a tightly focused beam of another laser that is, whose beam is scanned with a galvanometric mirror, and then you can write patterns of selectively annealed material. And what we use this for is, for instance, to carry out processing of quantum well structures, but also quantum dot structures. And here I'm showing you an example. This is the photoluminescence map of, in this case, if you look into B cross-section here, you have 4 spots here emitting at different wavelengths initially that were slightly annealed, so B1, B2, B3, B4. So the idea here was to tune the emission of these 4 spots to the emission of the first B1 spot. So we do this by iterative approach. In this case, by using 2 iterations, we could bring these 3 emissions close to this 1400, like you see in this last step. So between each processing step, you carry out photoluminescence measurements, and then you decide how much energy you need to take from your laser in order to induce this tuning effect, which is based on so-called quantum well intermixing. Another application of UV-based lasers is bandgap engineering that is based on the application of, in our case, excimer lasers. So you basically, in this case, you modify surface properties of materials, which is the first step of the process, and then in the second step, you carry out conventional rapid thermal annealing, and then you end up with wafer that can have a different emission of wavelengths, a different energy depending on processes, on parameters of lasers that have been used for this case. So we work on this in collaboration with various people that are interested in using multi-bandgap materials for integrated systems. There are various publications you can check if you're interested. And we also fabricated some superluminescent diode using this kind of approach. The last example that I want to show is using UV laser processing for silicon. So we are interested in physics and chemistry of surfaces. So in this case, by annealing a silicon on wafer that is placed either in methanol or in H2O2, we can induce a hydrophobic or hydrophilic surface of silicon. And this can happen in situ. You can change just environment and go from one type of surface to the other. And here you have an example how we created hydrophilic surface of silicon by irradiating this area through the mask, and then we dip the whole wafer in the solution with fluorescent stain biotin conjugated nanospheres that basically were able to attach themselves to unprocessed area of silicon, and the area that was processed was supposedly should be dark. We have some defects here, but that's basic concept of this approach. Okay, so let's go to the main subject of my presentation. What I will tell you a little bit is what is driving our interest in photocorrosion of functionalized gallium arsenide, aluminum gallium arsenide nano-heterostructures. I talk about stability of gallium arsenide in aqueous environment and photocorrosion on bulk versus superlattices or nano-heterostructures. There are important differences here that we take advantage of course. And I will address a little bit the issue of alkanethiol self-assembly monolayers on 3.5 semiconductors. I talk about biofunctionalization and give you examples of two applications where we use this process for photonic detection of bacteria, and we recently started working on monitoring bacterial reactions to antibiotic by using this approach. So you all know very well in semiconductor physics that when you go from three-dimensional structure to the surface, this loss of three-dimensional symmetry leads to formation of so-called surface states. So when you have a typical semiconductor and you deal with those surface states, so if you have a slightly doped or N-type material, the surface states here are really electron-philic. They like to trap some electrons. So typically what happens is that electrons from the bulk of material, they go to the surface, and then they create so-called depletion region of semiconductor, and with this related electric field. Now, when you work with when you are able to immobilize the surface of your semiconductor molecules that can either give down electron or can take electron, then you can modify the situation. So if you have a molecule like hydrogen and water or some hydrocarbons that can give electrons at the surface, so then those electrons that were initially trapped from the bulk, they are returning to the bulk of material. Therefore, this depletion region is narrowing, is relaxing in a sense. Therefore, this field becomes a little bit weaker. And on the other end, when you have electron-accepting molecules, the situation is opposite. So now you can imagine if you have a material that emits photoluminescence, and this region is playing an important role in the region where you excite carriers. So this situation with band bending will reflect on intensity of photoluminescence, because the strength of this electric field here will decide how much carriers are separated. So when you excite electron-hole pairs, so instead of allowing them to recombine and emit photoluminescence, you just separate them, and then you start seeing photoluminescence going down. So some time ago, we asked the question, can we use this effect to monitor reactions involving electrically charged molecules at surfaces of semiconductors? So we said, is it possible that you can design a photoluminescence emission-based 3-5 sensor or biosensor, if you will? But our focus, our interest was to find out if we can work with electrically charged molecules, how we can monitor their presence at the surface. So just to emphasize this, here's a sketch that describes roughly what you can expect when you think about using this kind of surface effect for sensing or biosensing application. So what you see here, you have what I just mentioned, depletion width and band bending, and the region near the surface of semiconductor that is drastically quickly changing in terms of concentration of ions. And the second thing is that you have typically, when you have an interface between semiconductor and electrolyte, typically Fermi level in N-type materials is slightly higher than electrochemical potential of electrolyte. Therefore, additional electrons from semiconductor would flow towards the surface, and therefore would contribute towards band bending of semiconductor. So what happens is that when you have electrons that flow towards the surface, and create this field, now we excite carriers. So now electrons will be repelled from the surface, the photoelectrons, and photoholes will be pushed towards the surface. And that's a problem, because in N-type gallium arsenide, this leads to so-called anodic photocorrosion that is described roughly by this formula. So typically, what you have here is a process that depends on presence of holes. So therefore, the higher concentration of holes at the surface, the faster photocorrosion of material can take place. So for that reason, gallium arsenide, even though it is interesting from the point of view of energy band for photovoltaic materials, has never been successfully used for this application because of that photocorrosion. So people would try to use various methods to stabilize the surface of 3-5 materials, and gallium arsenide in particular, and it is already more than 40 years that they discovered, for instance, that sulfur is very good material to stabilize, to neutralize some of those surface states at the surface of gallium arsenide. But in the same time, there was a lot of work in the 80s and the beginning of the 90s where they start using thiols. And thiols are interesting compounds because on one end, they have a sulfur, and on the other end, they can have a terminal group that can be designed to your liking, almost. Why it is important? Well, because on one hand, you can stabilize or somehow passivate surface of your semiconductor. On the other hand, and on the other end of this structure, you can create a molecule like this NH2, which has a strong affiliation towards proteins. So if you want to have a linker for proteins attached to the surface of semiconductor, this is a very interesting molecule. So our goal was to see if we can functionalize surface of gallium arsenide and can we detect bacteria that normally we know at most bacteria at pH more than 2 or 3 are negatively charged. So we work with many thiols, and we look into various combination of those thiols. And this is one of the more interesting thiols because here we have a so-called biotinylated thiol. So here is biotin. The reason that this is so interesting is because if you have a biotin, then you can think about a linker like neutravudine that can be used to create interface between your semiconductor and biotinylated antibody. Neutravudine is a molecule that has 4 pockets for catching biotin. So on one end, you can have a biotinylated thiol. On the other end, you can have a biotinylated antibody. So this was the beginning, and actually at that time, Zbig was working at NRC, and I was already at the university, and I asked him, can you get me sample of gallium arsenide that would be high quality, would emit photoluminescence very strongly, but would have very thin layer of gallium arsenide and aluminum gallium arsenide. And at that time, we observed a very interesting effect. We're trying to monitor functionalization of gallium arsenide with tiols. And in this case, we use HDT tile, hexadecan tile, and we observe that photoluminescence, if you measure of the photoluminescence of gallium arsenide exposed just to ethanol, goes very quickly down. So this is like experiment that takes like 18, 20 hours in the case. But when you expose gallium arsenide to a mixture of 2 millimolar HDT and ethanol, you see very quickly rising photoluminescence and then some stabilization of the signal. However, what we notice that this effect depended on what was excitation power of this experiment in this experiment. If you were working with a relatively excessively high excitation power, like in this case, 460 milliwatt per square centimeter, you never saw any increasing signal with time. It's only when you decrease the excitation density of excitation power to below 100 milliwatt per square centimeter that we start seeing some positive effect in terms of using attempting to tiolate surface of gallium arsenide. So the conclusion from this, and we published this in 2009, so it was quite time ago, was that, hey, intense photoluminescence prevents formation of robust tiol gallium arsenide interface. And at that time, we did not completely understand what was the mechanism behind of this behavior. So then, couple years later, we still start working, trying to understand this process. Then we look into some publication where people, they were talking about so-called photo-washing effect in gallium arsenide. So photo-washing effect in gallium arsenide, this was reported in 80s, end of 80s and 90s. People observed basically increasing signal of from gallium arsenide exposed to water environment and at the same time irradiated with white light. The white light, in this case, was important that you excite electron hole pairs. The rest was less important. And they call this photo washing effect because this was only observed when you were washing material, were flowing deionized water or water over gallium arsenide, and at the same time you excited electron hole pairs. So then more detailed studies, they show that actually this enhancement is related to formation of mostly gallium oxides, because arsenic oxides are very much easier dissolvable in water, and it was gallium oxide, and especially digallium trioxide, that was creating some positive effect in terms of stabilization of surface of gallium arsenide. So this increasing photoluminescence with time was explained as a partial passivation of gallium arsenide or partial neutralization of surface states of gallium arsenide. So now we go back to our experiment, and what we do here, we have in this case, you have an 8 nanometer gallium arsenide cap, you have 10 nanometer aluminum gallium arsenide, and then another 3 nanometer gallium arsenide. And we measure this as a function of time, just in deionized water, as a function of time. And you see initially some decrease of the signal, but there is a formation of characteristic maximum that takes place in this case, like within roughly 1 hour. And what is important here is that this effect was observed only when we excite our semiconductor for 1 second and then give 100-second break between next irradiation. Now, and we call this duty cycle. So when you increase the duty cycle and you go to 1 second irradiation in 10-second period, you see 2 maxima. You see 1 maximum, then a slow decay of the signal, slightly slower decay of the signal here, then another maximum, and then some sort of stabilization. When you go even to more aggressive duty cycle, you go to 5-second irradiation in 10 seconds, you only observe one maximum, roughly 1 maximum here, and then some structure, but not very well resolvable on this time-dependent photoluminescence signal. So obviously, and so you can see that within 1 hour, we start immediately linking the formation of this maximum with transition from gallium arsenide to aluminum gallium arsenide. And like in this case, we were suspecting that those two maxima are related to these two interfaces, going from A to B and from A to B here. So I have a picture that actually gives a little more information from the first round that was at 1 second per 100-second break, 100-second period. So you can easily see two maxima with this low region. So I can jump ahead and I will show you some XPS results and some more detailed chemical analysis that we carried out. So our interpretation of this is that these two maxima are related with these formation of these two interfaces, going from one to the other, and whereas this is related to slightly slower photocorrosion of 10 nanometer aluminum gallium arsenide. So this formation or presence of this interface here create very interesting situation for trying to see if we can measure photocorrosion dependent on external parameters like electric charge of molecules that would affect, for instance, band bending. So what you have here is that if you have just one interface and you start photocorroding this material, so you first should observe increasing photoluminescence because if you have this photo washing effect, formation of gallium oxide at the surface. But when you photocorrode all gallium arsenide and you hit aluminum gallium arsenide, the signal goes down. So just from observation of position of formation of this maximum here as a function of time for different external conditions, we start using as a way to measure presence of electrically charged molecule. Here is one example of XPS that we carried out. So first, let me just tell you about this. We have 5 samples that were measured up to 9 minutes, 20, 40, 60, and 70 minutes. Okay, so those are 5 different samples photocorroded for different period of time. And now, for reference sample, and we look into aluminum 2P region XPS data, and for reference signal, we don't see much here. Well, as you expect, because the surface is coated with a layer of digallium trioxide. But in case when you already etch aluminum gallium, when you etch already gallium arsenide and you are at the interface with aluminum gallium arsenide, you see that that formation of maximum that you can resolve 2 contributions here coming from aluminum gallium arsenide. And you can jump to case number 5, and you see there is a very nice reproducibility of this behavior between for 2 and for 5. Of course, one has to remember that XPS in-depth resolution of XPS is only 10 nanometer or so. So we have here a little bit a problem with sharp resolution of the interface. Nevertheless, you can conclude from this data about chemical composition of material that you are probing when you go in depth. So one more example of photocorrosion, I will show you another piece of photocorrosion obtained for the sample that was done, was grown by MBE. Again, is big contribution here. So what you have here is a 20 nanometer gallium arsenide, and then you have a 1 nanometer gallium arsenide, 2, 4, 6, 8, 10, 20, 30, 40, 50, and 60, and each of them are divided by 20 nanometer of aluminum gallium arsenide. So now you see what happens when you start photocorroding this material. And this experiment was carried out for a relatively long period of time. Here we have a total time is up to 18 hours in this case. So what you can see easily, you can see 11 maxima that we associate with transition from gallium arsenide to aluminum gallium arsenide each time we hit this interface. On the picture on the right, we created a plot showing total microstructure thickness that was obtained from known parameters of growing this structure, and the maximum position that we obtained from this figure here. So quite linear dependence. That is one thing. But second thing, what I would like to point out here is that, this, because this photocorrosion is proceeded in a controlled way, and it's at such a slow rate, you can easily resolve here 1 nanometer thick gallium arsenide, or contribution of 1 nanometer thick gallium arsenide. I think this could be even better because I didn't mention here to obtain all of this maxima here, we had to use not deionized water because it would be too slow. You use ammonium hydroxide. And only in this moment, we could speed up a little bit the process of photocorrosion. The other interesting thing is that, of course, there is some dark photocorrosion. If you don't irradiate your material and you put it in DI water for, like in this case, experiment was carried out for 48 hours. So we compare just freshly etched sample with 48 hours exposed to DI water and to phosphate buffer saline solution that we use in our biological experiment. So you see the sigma RMS is slightly increasing. It's not remaining the same, but this is 48-hour experiment. When you do the same thing for material that is functionalized with tile, so use some tile structure, like in this case, we have a MHDA self-assembly monolayer. Also, 48-hour experiment, you see that sigma RMS also increases, but it's not as rough as material not protected with self-assembly monolayer. So obviously, there are differences here that are immediately showing up, depending on how you functionalize your material. So what I want to, oops, what happened here? Sorry. Sorry about that. What I wanted to show here, what I wanted to show here is this picture that basically summarizes what is happening and is giving you a little bit idea about dimensions of the architecture that we deal with. So here there is an interface. Here is our surface of semiconductor, band bending, and then in terms of charge accumulation. And you have here tile, then biotin, then neutravidin and biotin-related antibody, then something that schematically we believe this is representing bacteria that is negatively charged. So you can see this is not up to scale, but roughly the distances that we talk about here, in this case, this is roughly 2 nanometer, neutravidin is roughly 5 nanometer, and antibody is 10 nanometer. So this is our range that we talk about interaction between electrically charged molecule immobilized on functional surface of semiconductor. Of course, it is not necessary that only electrostatic interaction you have to think of. You may have also some charge transfer. That's another thing, because we learn from some other experiments that bacteria immobilized on various surfaces can also take electric charge from the surface or give away electric charge. So now let me go to examples of application of this effect for detection of two types of bacteria. So we have our conventional architecture that we apply. It consists of biotin-related tiles, neutravidin, and biotin-related antibody. Here's an optical image of a bacteria that was immobilized from 10 to 6 colony-forming unit per milliliter of Escherichia coli, and then fluorescence image that was obtained by attaching a fluorescent stain antibody to already immobilized bacteria. So for typical 10 to 6 of CFU per ml of E. coli, our surface concentration is roughly 2,500 bacteria per millimeter square. This unit is basically corresponding to that, roughly 2,000. So our sensitivity is in the range of at least 100 bacteria per millimeter square. We notice that we cannot detect if we have a less than 100 bacteria per millimeter square of our biosensor. So here's the issue. I mean, here's the challenge, is because you can, the efficiency of immobilization of bacteria may depend on the architecture that you apply, but also procedure that you apply. So the more efficient this procedure is, the better sensitivity you can achieve. So that's what we basically are interested in right now. But before I tell you more, I should show you some examples of runs, of photoluminescence runs as a function of time for this case. So, like, if you have an antibody functional surface and expose this to PBS, then this first maximum occurs within 10, 15 minutes. Then, if you have a 10 to 3, you see this position is here, 10 to 5, this position is here. So, from many runs like this, then you can make your statistics. And, like in this case, for E. coli bacteria, we demonstrate that you can detect quite reasonably 10 to 3 CFU per ml. We would like to be a little bit better, like 10 to 2. And I think, like I just said, this depends on efficiency of immobilization bacteria with architecture that is applied. And this is not completely well covered yet. We are trying to see how this can be improved. One thing to remember is that electrostatic interaction of bacteria with our antibody is related to zeta potential of bacteria. So you can imagine that if the higher zeta potential of bacteria, minus, which typically is 10, 15, 20 millivolt, the higher interaction can be, therefore more efficient and faster immobilization of bacteria. Another example that I want to show is detecting of Legionella pneumophila, which is in different bacteria, and this is of our main interest in this research because Legionella pneumophila, probably you have heard, this is one of the problem of water processing station, and once in a while you hear about people catching Legionellosis, which is kind of bacterial disease that seems with a symptom like flu, but it is not flu, it is just bacterial disease. And last time, I think it was 2 years or 3 years ago in Quebec City, when you've heard about several people die. So we are actually focused on using this for detection of Legionella in water. We have a group of people working on collecting water samples, filtering, and sending to flow cell where we measure response of Legionella to this surface effect. In this case, so far we were able to publish, to demonstrate in a reproducible way that you can detect 10 to 4 bacteria per ml, and we verified that it is indeed related to zeta potential of Legionella that is slightly weaker than zeta potential of E. coli. The last thing that I want to mention about the application of this is our more recent results that are focused on using this effect for monitoring behavior of bacteria. So first of all, you have to learn how to grow bacteria on gallium arsenide. And like I said in the abstract, yes, bacteria can grow on gallium arsenide. If you functionalize surface of gallium arsenide in such a way that the surface that the distance at which you want to grow bacteria from the surface is not 0, but at least a couple nanometers, then a negative effect of oxides that are formed, could be arsenic oxide or gallium oxide, on the well-being of bacteria are minimized. Because this is what can interact with bacteria and can prevent bacteria willing to grow. So we create the conditions that you can grow bacteria starting from 10 to 3 or from 10 to 4, and within a couple hours you can have a 10 to 7, 10 to 8 bacteria per milliliter concentration in the surface. And so this is done, of course, in the presence of food for bacteria. So what we have here, we measure photoluminescence when bacteria is growing with a food LB medium. So this is a red curve. So basically, if you see this photoluminescence doesn't want to decay, means that we still have a large concentration of bacteria and a large concentration of negative charge at the surface. In contrast, when you have a bacteria that you inject, but previously you just kill this bacteria with UV light, in the blue line, so the maximum occurs somewhere here. But the bacteria that you're working here is sensitive to antibiotics, to both to ciprofloxacin and to penicillin. So 2 cases that you have for bacteria here, if it is exposed to penicillin, even in the presence of calcium medium, the maximum occurs very quickly and bacteria decays. So yeah, this is under review. We submitted this to a biological journal. And I think this is interesting because with this technique, we can demonstrate the reaction of bacteria to antibiotic within less than 3 hours. So my colleague, microbiologist, tells me that, yes, this is strategically very important because the doctor offices or places in the clinical environment, they want to detect reaction of bacteria to antibiotic within 1 shift. 1 shift means 8-hour working person in the lab. You cannot leave this for the next day because then it's a completely different story. So being able to do this in 3 hours seems to be very attractive. I think I'm running towards the end of my presentation. I just want to summarize. So first of all, I hope that I was able to show you that 3-5 materials are, on one hand, they are well, you know it very well. They are interesting for optoelectronic applications, for microelectronic applications, etc. But on the other hand, we know that these 3-5 materials are very sensitive to moisture. What we develop here is develop technique that allows to investigate sensitivity of those materials at nanoscale. And as you have seen, the trick is that you are not irradiating material all the time. Like in classical experiments where people they use photo etching, for instance, for 3-dimensional structuring of semiconductors. If you go to papers from 80s and 90s, they were able to carve 1 micrometer of semiconductor within 1 minute. Here we talk about 10 nanometer within 1 hour, or something like this. So yes, we can control this at a nanoscale. Therefore, we can see very interesting effects like sensitivity of photocorrosion to those external electrically charged molecules. In this case, I was showing effect of reaction to E. coli and Legionella pneumophila, but there are many. We have in the lab very interesting other results where we show, depending on what charge, electric charge molecules they carry, and we immobilize them on the surface, and then we see either positive or negative reaction. Here, what you can say is that bacteria is preventing, you can say the bacteria is preventing corrosion of gallium arsenide. Yes, because it slows down the photocorrosion process. And you have seen the surface morphology, basically, of photocorroding material of functionalized photocorroding material is quite smooth. And we demonstrate that we can detect E. coli and Legionella pneumophila as 2 examples of bacteria with sensitivities that are very attractive, although we would like to to go at least for one order better, and that's what we are working on. We would like to detect at least 10 to 3 or maybe 10 to 2 of Legionella pneumophila per milliliter. So this is our main challenge right now. I didn't talk about this, but we applied for patent where basically if you can have a stack of materials like this, you can imagine that, and what we need is interfaces. So when you use one interface and you have 29 desti left, you can imagine that you can clean the surface and refunctionalize your gallium arsenide layer again, and then carry out in situ without removing biochip another experiment. So theoretically, we think that we should be able to get more than 10, maybe 20 experiments from one biochip. If this turns to be true, then according to calculations that we did, the cost of biochip becomes negligible in this case, to the cost of reagents that you have to use to complete experiments. So this is an interesting paradox that on one hand, this biochip may drive the whole technology, but on the other hand, it may be in cost-wise, it would be negligible to the whole cost of experiment. And so another thing is that we know that these 3-5 materials, gallium arsenide, aluminum gallium arsenide, they are very well developed. So this is like almost like light-emitting diode material. So even from this point of view, it offers cost-attractive solution. So the last slide I want to, of course, there are students that are involved here, so I just happen to be talking about them. But mostly the results that I was showing here were obtained by Srivatsa et al., who is a PhD student still working on his thesis, Reza Azizian, and Nas Nazemi, who did a lot of this experiments involving detection of measuring reaction of bacteria to antibiotic. And postdoctoral fellow, Jia Huang, she is at Wuhan University of Technology right now. She returned there. Neng Liu, who was our postdoctoral fellow. And of course, all of this would be impossible without collaboration with Professor Frost from microbiology, from Faculty of Medicine of our university, with whom we have several projects, and we co-supervise. For instance, ELNAS was co-supervised with Eric Zbeck, who was kind to provide me some material when he was still working at NRC. But we are keen to test your material from Wien, which is probably happening this fall. And of course, some colleagues from France with whom I have some students that we could supervise. So I would stop here and thank you for your attention.
Well, thank you very much, Jan. We'll talk you up to questions. Here? Well, like I kind of thought at a certain point that I did understand, and I have a little bit of a doubt. So the peaks in the photoluminescence which you observe are, I imagine basically the electron hole pair no longer recombine as efficiently as they could. So either the electric field is not splitting them as efficiently, or the recombination on the surface is higher. Which one is that? Because you observe the peak when you hit the aluminum gallium arsenide, right? The maximum happens.
Well, first of all, this is not peak, this is the maximum. Yes? So we observe temporal behavior of photoluminescence from the system as a function of time. So this is related to photocorrosion of material.
Right.
Okay. Now, but since photocorrosion, the rate of photocorrosion depends on band bending of semiconductor. Therefore, you can translate this into how much electric charge you have to present at the surface of semiconductor in order to achieve certain rate of photocorrosion.
Okay.
So it is photocorrosion. It is electric charge modified photocorrosion. But people have done a lot of photocorrosion studies in the past. But all of these measurements were done so fast. They were just observing very quick removal of material. here, because we pick up this issue of measuring photocorrosion at very low rate, so we simply irradiate, create electron hole pairs, and then allow for system to relax and diffuse, for instance, product of reaction to the environment. I didn't talk about here about that. We can continuously move your liquid environment in the flow cell, but this is also important. So intensity and time between two pulses that you allow, or two period of irradiation that you create electron hole pairs. Otherwise, everything is swamp. Everything goes so fast.
Well, okay. I mean, I think it was Wolfgang Pauli who is credited for the statement that God created bulk, but the surfaces were created by devil. It's pretty brave what you're doing here. I think for the nanotechnology, it's interesting information. And as we get those things smaller and smaller, surfaces are really becoming most of the action, and there's so much happening, particularly if we have bacteria as well. Any other questions? Yeah. Then you see. That's important.
My question is, have you tested, I know, to the big through your layers, and you have done gas, AlGaAs there. Have you done any tests when you would have different composition in your gas layer, for example, or different material together?
No, I think we haven't done much other systems. 3.5, some other 3.5 nano-heterostructures. The point here is that we are taking advantage of photoluminescence that is increasing in water environment from material from gallium arsenide. But in the same time, because our gallium arsenide is very thin, so photocorrosion of that material occurs in a reasonable period of time. Of course, we could wait a couple of hours, you see the same thing, but it's not interesting. We want to see this within 10, 20 minutes because there is not enough of gallium arsenide. And it happens that when you have aluminum gallium arsenide, the photocorrosion there goes a little bit slower. So this is related to two things. And one is that band gap energy of gallium arsenide, aluminum gallium arsenide is a little bit wider, and we're still using same energy to excite carriers. So efficiency of electron hole pairs generation, aluminum gallium arsenide is weaker in this case. And the other thing is that you have a material that can corrode, gallium arsenide is you have to look into surface recommendation velocity. So if you look into from that perspective, then you hit different surface recommendation velocity on gallium arsenide, aluminum gallium arsenide. It happens that this works to our advantage because in gallium arsenide we go up, in aluminum gallium arsenide we go down. So we observe formation of maximum within an attractive period of time. Now we try to how we can modify position of this maximum with external parameters like electric charge. Other system I think should work if you can generate this kind of situation.
All right.
How selective is the platform? Like if they have the multiple bacteria, so can you detect selectively one particular bacteria?
Our approach, this is a good question, but our approach is based on what biology is giving us. So we say, okay, what biology is offering us today? There are a couple of things. The most trivial and most obvious seem to be antibody. So we use antibody, and that's how we detect our bacteria. We apply specific antibody for this bacteria. And of course, when you think about this, then another extension of this would be creating of array of regions with different antibody, and then do so-called multiplexing. So you'd like to detect different bacteria at the same time, and then be selective. Yes, antibody, that's one thing. But you can, and we work a little bit with other architecture, for instance, aptamers. They're very interesting because antibodies are more sensitive to temperature, and they are not necessarily that good to some other conditions, perhaps, that you'd like to see. So, for instance, aptamers are much robust, much better molecules for this. However, there are only a few aptamers that you can buy at a reasonable cost, let's say, that you can play with this and then hope that this would be better than what you have today with antibody.
That's going to be tricky to throw the order, but maybe we can do something more.
So I'm not sure if I missed this, but when you have the bacteria attached to the antibody, does that attachment improve the surface passivation, or could the bacteria that's now attached to the surface be absorbing the light and that causing the delay?
It's a very good question, yeah. So what we have an antibody functionalized surface. So this is our starting point. And by that time, we already have taken care of partial passivation, at least because we have sulfur involved in the reaction, and we have antibody there sitting and waiting to catch bacteria. But now, bacteria is when it is immobilized at the surface of antibody, is a negatively charged object. Now, what happens with bacteria in environment? There are two things that we don't have a clear picture here yet, but we think there are two things that are happening. First of all, negatively charged bacteria in any environment, liquid environment, should become decorated with positively charged ions. That's what normally you would think, intuitively from electrical interaction. So we think that one way that we slow down photocorrosion is because those positively charged molecules that are sitting, ions that are decorating bacteria, they prevent holes, the reduced number of holes arriving to the surface. So that's one thing that can be used as explanation. But the second thing is that we learned that bacteria immobilized by thiols can transfer charge, actually, through those thiols to the surface. And there are experiments where they have shown that depending on type of bacteria and type of environment, they see that bacteria either can transfer part of its charge to the surface to which it is attached, or can take some charge. So we don't have a clear, we are working on model, trying to get some semi-quantitative description of this, but in that model, those are two possible channels. Probably there will be more than that, but yeah, that's. Do you
think, so with the charge transfer, do you think if you added something like a protein pump that could transfer protons down the thiol, that might be able to then affect the photocorrosion as well?
Again, very good question. Where's this from?
That's what we are here for.
Yeah, we are working on. We are trying to decorate bacteria with negative charge. Most people in biology, in microbiology, they say, why would you do this? They want the opposite. They don't want the bacteria to stick, to the surface. And we have some idea already. We did some experiments, and we decorate bacteria with negatively charged molecules. And this enhances, actually, the effect. So that's one of our strategy, actually, that we are working on to increase sensitivity.
All right. Now we have like 4 o'clock, so if there are any questions, but some of you want to leave because of some other commitments, please go ahead. Anything else you would like to ask? Well, all right. If not, then let's thank Jan once again for this very interesting talk.